Perfect. Sorry for the additive problem. Thank you all for being here. So we keep the intro short because we're a bit late, but we're very, very lucky to welcome Frances Cooper here. Frances is an associate professor in earth science at UCL, and she's one of the two distinguished lecturers from the UK and Ireland Mineralogical societies this year. Oh yeah, Frances work on many things, but in particular all things copper. And today she will talk about how we can use copper to track groundwater flow in Chile. Thanks, Frances.
Thank you very much, Thomas. Thank you very much for the invitation. It's really lovely to be here. I've never been to Camborne School of Mines, and it's really nice to get away from London for a couple of days and enjoy the beautiful scenery of Cornwall. So thank you very much for the invitation. I will just do a quick plug for the Mineralogical Society of the UK and Ireland because they are sponsoring this lecture tour that I'm giving this year. Great organisation, and if you're a student, membership is free while you're a student, and I believe that free membership continues for at least a year after you've graduated. And it comes with all sorts of different bursaries for attending conferences and doing different things. And there are also different magazine publications generated from the MinSoc that are worth getting. And you also get a copy of Elements magazine delivered to you 4 times a year, which is always beautiful and well worth having. So if you haven't already signed up for the MinSoc, there's my plug that I'm required to give at the beginning of these talks. So my background, just briefly, is not actually in economic geology. I started out really studying large-scale tectonic processes, originally in the Western USA, then in the Himalayas for quite a few years. And it wasn't until I started working on a project with BHP back in 2012 that I started thinking about ore deposits, particularly copper deposits. So I come at all of this, this work from a sort of outsider's perspective, trying to understand mineral deposits and ore formation slightly from a sort of outsider's point of view. And the talk I'm going to give today brings together quite a lot of different sort of basic geology, but trying to think about the interaction between tectonics and climate in particular, and the role that that plays in specifically in the enrichment of deposits. And we'll be focusing in the central Andes in northern Chile. Okay, so I know I'm in the Camborne School of Mines, so some of this may seem a little bit, you've heard it all before. But just to give you a little bit of a background for why this is important, why do we need copper? I mean, copper is pretty fundamental to almost everything that we use, particularly in the last 100 years with the development of electricity and all the different mod cons that we have. We need copper pretty much for everything. It's an ideal conductor. It forms the base for some of the primary alloys that we use, such as brass and bronze. And one of the nice things about copper is that it is a sustainable metal. However, as we will discuss, despite the fact it's 100% recyclable, we don't actually recycle as much of it as we should. But even if we did, that probably wouldn't be enough to see us through the big changes that we require if we really want to change our economy over the coming years to move away from fossil fuels. So why do we need more copper? Now, this is going back a few years, but I still think it's worth just reading this out. So this is back from the glory days of Boris Johnson as our Prime Minister, and the net zero strategy published by the government in 2021. And I'm just going to read it out, not in a Boris Johnson voice. In 2050, we will still be driving cars, flying planes and heating our homes, but our cars will be electric, gliding silently around our cities. Our planes will be zero emission, allowing us to fly guilt-free, and our homes will be heated by cheap, reliable power drawn from the winds of the North Sea. It sounds idyllic. Things haven't really changed. We have a new government, but actually many of the aims and ambitions haven't really changed, although obviously economically, whether they're realistic is another matter. I'm not going to get into that. But the Labour government also has a similar strategy, make Britain a clean energy superpower, to cut jobs, to cut bills, create jobs, deliver security. They definitely all know that. But there's this general sense that we need to increase our reliability on electricity, generated power and vehicles, and less on fossil fuels. And I think there's, despite all the changes in the world at the moment, that is still in the background, that is something that we need to do. And so what does this actually mean in terms of the metals? And in particular, we're thinking about copper today. So just as an example, when we think about an electric vehicle, a typical petrol engine, internal combustion engine vehicle, and this is an American diagram, so it's in pounds, I'm afraid. A typical petrol vehicle requires about 48 pounds of copper, whereas a hybrid electric vehicle is almost double that, 88 pounds of copper. A fully battery electric vehicle, your Elon Musk Tesla, is 183 pounds of copper. So almost 4 times more copper is required for an electric vehicle. So that Boris Johnson's idea that we're all just going to replace like for like and have the same number of cars and drive around guilt-free is unrealistic if we really consider how much extra metal we're going to require. And when it comes to power, renewable energy is 5 times more copper intensive than conventional systems. So examples, conventional or nuclear or hydropower, onshore wind, offshore wind, photovoltaics, so solar panels, are all much, much more copper intensive. So we need to find more copper. This is another diagram sort of showing future projected trends in copper usage. So this is kind of our current usage over time. So 2020, here we are in 2025, projected to go up if we kind of carry on as we are. And then various projections depending on how much we want to increase our renewable energy generation, expanding our grid, or how much we want to increase the number of electric vehicles and chargers that we generate. So all of this is speculation, but various projections, all of which are greater than our current usage. And this is our current copper production up here, so 22 million megatons. And if that stays flat, then we're going to hit a potential deficit only about 10 years from now. And there are lots of different versions of this plot, but the underlying fact doesn't really change, that our current production rates are not going to meet the needs if we really do want to undergo this big energy transition that we say we want to. So demand is projected to soon outstrip supply. Maintaining the current rate of production is not sufficient, and we really do need to find new deposits. Again, I'm in the Campbell School of Mines, so none of this is probably new to anybody here. So where do we find copper then? We need more of it. Where do we find it? This map here from Silico 2012 shows some of the major copper generating regions in the world. And these are mostly like the super giant copper deposits and districts that have more than 24 million tons of copper. And the vast majority of the copper that we use comes from what are known as porphyry copper deposits. And those are the ones in red. There are some other ones on here, like sediment-hosted stratiform copper deposits, particularly in the Central African copper belt, some in Central Europe. There are others, IOCG, iron or copper gold, but the vast majority come from what are called porphyry copper deposits. So we're going to think a bit more about what those are. So you can probably see from the spatial distribution of these deposits around the planet that they tend to form in convergent margin settings dominantly, and they are associated with subduction zones. And they essentially are a function of melting of material just above a subduction zone in the mantle wedge. You get a lot of fluids being subducted down with the subducting plate, generating melts down here in the mantle wedge. They are ascending up through the crust and they're fractionating as they go. And basically, the porphyry copper deposits themselves are just these little bits at the very, very, very top, which are forming the very, very tops of these granitic systems above these subduction zones. And they're basically at the very, very top because they're very, very hydrous. So we have a lot of fluids involved in these systems. So they're magmatic hydrothermal deposits. And these fluids can work their way up, and they'll work their way up to the very tippy top of the system to form the deposits in the very near surface environment. And the typical depth of porphyry copper systems is only a few kilometers, 2 to 5 kilometers on average. So they're really forming kind of just in the roots of volcanoes, very close to the surface. Now, this is a very cheesy video that I found on YouTube, but it does give some quite a good overview of how these these deposits form. So taking this with a pinch of salt, here's our magma at depth in the crust, moving upwards through the crust. And here's our volcano up at the surface. So we're up in the very shallow environment here, in this just below the volcanic system here. We've got a lot of water coming into the system. We've got magmatic fluids coming from depth. We've also got meteoric water at the surface. We have a lot of fluid in the system, and we have a lot of copper. And basically, rather than erupting out of the volcano, the copper is actually trapped in the subsurface beneath the volcano, where it can form an ore deposit. So why do we work so much in Chile? Well, Chile is a land with lots of volcanoes. This is a photo of us from 2012 when we first went out. This is Laura Evenstar, some of you may know her, and two of our PhD students at the time, Marit and Brad, when they were just starting out. And this is the Parinacota volcano. We're up on the border between Bolivia and Chile here. So Chile is a place absolutely full of volcanoes, full of alpaca. I have to throw this photo in because it's just a stunning photograph of Chile. And it has a lot of copper. So this is a Google Earth view now, looking north in northern Chile. So this is Chile here. It's very long and thin. We've got Peru up here, just as you turn the oroclinal bend. And then we have Bolivia over here. So this is the Andean Plateau, the Altiplano. And then to the east of that, we get into the Amazon basin, where you can see it's very, very green and lush. And this area, by contrast, is incredibly barren, very, very dry. The Atacama Desert is the driest places on the planet. But what we can see through here is an entire belt. This isn't every single deposit. This is the majority of the deposits. And you can see that they're pretty much aligned parallel to the subduction zone through this region. And they're differentiated here into porphyry copper dominant systems in the green triangles, porphyry copper molybdenum deposits, and porphyry copper gold deposits in red. So there's only a handful of the gold deposits. And the majority are either just pure copper, or a lot of them actually have copper and molybdenum together. The deposits we're going to be focusing on today are Spence, right here, Cerro Colorado up here. And I'm going to show you a picture of Chuquicamata here in just a second, and we'll come back and think more about them. So just a little bit more about what these systems are and how we think about them. So as I already mentioned, they're the world's major source of copper. The amount that they produce sort of varies depending on who you ask, but generally about 65 to 75% of production is from porphyry copper deposits, 95% of molybdenum production, and they can host other metals such as gold, silver, and sometimes things like rhenium, tellurium, and platinum group elements. And the copper is primarily hosted in sulfides, like chalcopyrite is the primary sulfide in the formation of these deposits, and the molybdenum tends to form in what's known as molybdenite. They also have a huge amount of iron sulfide in them, pyrite, which is going to be very important with thinking about what we're thinking about today. And this is a sort of schematic based on a Dick Sillertone paper from 2010. Again, just sort of illustrating the idea that you've got this sort of big granitic batholith, maybe formed over multiple generations of intrusion and emplacement. And at the very tippy tops of these systems is where you actually get the porphyry deposits themselves. And that's because these fluids have been able to kind of work their way up to the very top. And that's where they tend to get trapped at the very top of the system. And characteristically, they're always associated with quite a big hydrothermal alteration zone, which is shown here in green. One of the really defining characteristics of porphyry copper deposits is that they have incredibly low concentrations of copper. So typically less than 1% copper. And I think the current production cutoff grade is about, I think it's 0.5 or 0.53%. So really, really low grades of copper. This is a photograph of some drill core from Spence mine in Chile. And this is a classic hypogene mineralization here, which is like the primary copper mineralization. So you can see it's got the classic porphyritic texture, which basically means it's got some big phenocrysts surrounded by a fine-grained matrix. It's crisscrossed by a lot of quartz veins, which is demonstrating all the fluids that have come through. But it's very hard to actually pick out much copper in there. You can hopefully just about see There's a bit of gold colouring there, and that is a little bit of chalcopyrite in that quartz vein. But a lot of this is barren. There's some disseminated copper through here, but actually the majority of that rock doesn't really have much copper in it. So this is a problem. Basically, porphyry copper deposits are low grade and high tonnage. I don't know if any of you have seen this photo before. There's a guy called Dylan Marsh who has a website where he has taken photographs of old mining pits that are no longer in use. So this is Palabora mine in South Africa. And Palabora mine in South Africa is 1.9 kilometers long, 1.65 kilometers wide. It was 800 meters deep when they finished mining it. You can see there's obviously been quite a lot of landslip since mining finished. Over its lifetime, they mined 4.1 million tons of copper at an average grade of 0.7 to 1%, which is actually on the high end of what is often considered to be acceptable today. And what he's done is he's photoshopped in a sphere of copper representing 4.1 million tons of copper. So you can get a sense of the amount of rock that needs to be removed in order to generate that amount of copper. So this is, in terms of the future of mining and sustainability, this is a big problem, that we have to extract so much rock in order to gain such a small amount of metal. And so this results in some very, very large holes in the ground. So this is the photo I took at Chuquicamata, which is one of the biggest copper mines in the world in northern Chile. 4.5 kilometers long, 3.5 kilometers wide, and 850 meters deep at the time that I went, and produces about 650 megatons of copper per year. And the year I went, I think this was in 2014, they were actually just in the process of switching to underground mining. So they'd got to the point with this pit that it was so deep, the only way you could go any deeper as an open pit would be to widen it at the top. But they couldn't really do that anymore, so they switched to underground mining. And Chuquicamata has been in production for over 100 years. So this is an example of one of the biggest mines in the world. And it's sort of easier to do that when you're out in the Atacama Desert and there isn't very much around. Just for scale, I'll go back. The little, again, I'm in Campbell School of Mines, so I feel like you already all know this. The little tiny micro machines there are these giant monster trucks. So just for scale, we'll zoom in a little bit so you can see them here. They still look quite small, but in reality, this is the size of these things. So the scale of these pits is absolutely ridiculous. And I'm just going to do a quick comparison for you so you can get a sense, because it's really hard to get a good sense of the scale until you compare it with somewhere that you know well. So here's the rim of the Chuquicamata pit. And now we're going to fly all the way across the Atlantic northwards to Penryn. And it's just mind-blowing because you just really don't get that sense of scale. And when you go there, there are no trees. There are really very few buildings, and it's almost impossible to get a good sense of that scale until you map it onto somewhere that you're familiar with. And you just realize that if we need to extract copper from things that are that low grade, we're going to very quickly run into all sorts of political, social, environmental considerations and issues. So finding really high grade copper deposits is really vital to minimizing the impacts of mining. So a lot of the work that I've been doing over the last few years is trying to sort of think about how we get the highest grade copper deposits, and therefore in mineral exploration terms, where we might go looking to find the highest grade deposits. So the highest copper grades in these porphyry copper deposits are typically achieved through secondary enrichment processes. So that primary mineralization, we were talking about grades of 1% or lower on average. And the way that you generally get higher grades than that is by a secondary enrichment process. And really what that means is that you've exhumed that deposit to the surface or the near surface environment, and you're essentially weathering it in place in the near surface environment. So you've got oxygenated meteoric water is percolating down through that deposit. It's dissolving those primary sulfide minerals, liberating the copper into solution, and that copper then gets reprecipitated as new sulfides or oxides in a much more concentrated enrichment zone, or blanket it's often referred to. And that is the primary way that enrichment tends, that high-grade deposits are formed. And that's traditionally how the ones that we've been after, or mining companies have been looking for. So how does this work? So here's the continuation of our cheesy YouTube video. So now we've removed the volcano, we've eroded the surface, we've got meteoric water percolating down through those primary sulfides, that's our chalcopyrite, and it gets dissolved by the oxygenated meteoric water. We liberate the copper into solution, we get sulfuric acid as a byproduct, and then we end up with an enriched zone here. So this is our secondary sulfide copper zone or enrichment blanket. So this is where we might have grades of maybe 2%, sometimes they could be 3% copper. Still sounds quite low, but it's considerably better than what we had before. And the other nice thing about that is that it's in a nice condensed zone. You can imagine if you're a mining company, it's all in one fairly flat zone. And the reason that it tends to stop and form in this kind of blanket is it's controlled by the position of the water table. So these are the kind of minerals that we would see. So in the primary chalcopyrite from the original hypogene mineralization, that is what's being dissolved by meteoric water. And in that, we're getting sort of typical grades of less than 1%. By weathering at the surface and oxygenating and liberating that copper, we generate secondary sulfides, such as chalcocite. And above the water table in the oxygenated zone, we'll get secondary oxides and carbonates like cuprite and malachite. So the water table here acts as a kind of redox boundary. So that liberated copper, as it percolates its way down, if it precipitates new minerals below the water table in the reducing zone, you'll get secondary sulfides like chalcocite. If it reprecipitates above the water table in the oxygenated zone, you'll get secondary oxides and carbonates. So this process requires water, clearly. So then why are there so many supergene enriched deposits in northern Chile? The Western Andean margin, otherwise known as the Atacama Desert, is one of the driest places on Earth, with mean annual rainfall today less than 50 millimeters per year. Compared with the wet southwest. I hope that this is Penryn, because BBC News told me it was, that this was flooding here. So the average annual rainfall where we are today is 1,000 millimeters per year, just as a comparison. So why is the Atacama Desert so dry? There are a variety of reasons, and the interplay between them is still not fully understood. It's partly because the latitude of the Atacama coincides with a region of high pressure, where we have big convection cells in the upper atmosphere, and we get downwelling warm air just around the latitude of the Atacama, which basically generates high pressure conditions. We also have onshore winds that come off the very cold Pacific Ocean to the west. There are very cold upwelling currents in the Pacific, which means that the ocean there, because it's very cold, you don't pick up a huge amount of water from the ocean. So the winds that blow off the Pacific here tend to be quite dry. And then thirdly, we have the potential effect of the Andes Mountains themselves that act as a rain shadow for water from the very wet Amazon basin to the east. Any rain that's trying to come westwards hit the orographic barrier of the Andes Mountains and are rained onto the Andes. And by the time they get the other side of the Andes, they've run out of water. So basically, there is sort of a perfect combination of three different parameters in this area. And then this is just a photo that I have to put in. There are these incredible chinchorro mummies. Some have been carbon dated to about 7,000 BC. They are still to this day found sometimes out in the desert of the Atacama, just to demonstrate just how dry it's been for such a long time. So tracking the water table. So as I say, the process of supergene enrichment and leaching of these deposits is directly related to the movement of water through these systems. And drying out the climate can directly affect the position of the water table. So we can track the relative movement of the water table by dating the precipitation of hematite, which is iron oxide, which is basically a byproduct of that leaching process. So I'm going to show a little video to demonstrate this in a second. But you imagine you start off with your copper iron sulfide, which is chalcopyrite. You liberate that copper into solution, and the sulfur goes into sulfuric acid, but eventually will reprecipitate as secondary sulfides. You're left with iron, basically. The iron's pretty immobile. It doesn't move very far. It pretty much stays in place and becomes oxidized by the meteoric water. So what you get left in place is a zone at the top above your enrichment blanket, which is known as the leached cap. So here's a little cartoon continuation to show you that. So there's our primary chalcopyrite. It's being dissolved. We liberate the copper. The sulfuric acid the sulfur goes into making sulfuric acid and eventually secondary sulfides. And what we're left with above is pretty immobile iron, is oxygenated, and we get lots of hematite. In some places, it can also be goethite. In Chile, where I was working, it was pretty much all hematite. And so this is that same diagram again, showing this is our secondary sulfide blanket, where we get the much higher grades of copper and secondary sulfides, and then just above in some secondary oxides. But above that, we have what's known as the leach cap, which is pretty much all hematite left over. So what I'm going to talk about is how we can use the precipitation of hematite in these leach caps to tell us something about relative motion of the water table, and also a little bit something about where that water might be coming from and how that fits in with our understanding of the changing climate in this region. So we're going to be focusing on two deposits. One is Cerro Colorado up here in the far north of Chile. So here's the border with Peru, here's Bolivia. So we're up in the very far north. And Cerro Colorado sits up here on the kind of western Andean margin. So we're not up on the really high elevations here, but we're kind of on the flanks of the Andes here, compared with Spence over here. And Spence very much sits out in the middle of the Central Valley. So this is in a big sedimentary basin here. So we're in two quite different parts of the system. Here we're on the side of the mountains. Here we're kind of out in the basin. But another thing, oh, and then we're quite close to Chuquicamata. So Chuquicamata is actually just next to Calama right here. And something to bear in mind here is that there's a lineament along here called the Antofagasta-Calama lineament, which is fairly poorly understood. There's some evidence that it actually is a strike-slip fault, that there's been some strike-slip motion on this system, and it's actually quite a long-lived system. But there's some kind of potential fracture or through the crust in this area, and Spence just sits directly along that system. So how do we track the water table? So the great thing about working in an ore deposit with a mining company is you get access to drill core. And drill cores are amazing because you get vertical profiles through the crust that you can't really get elsewhere very easily. So what we were able to do is to collect vertical drill holes through both deposits, Spence and Cerro Colorado, and we could then sample hematite that had precipitated in the leach cap in each one and get a depth profile through each of those leach caps. And you can really see this is a photograph taken of Cerro Colorado back in the 1990s. It doesn't look like that now. A lot of it is, the pit is much, much bigger now. A couple of features to point out here. One is that you can actually see, I don't know how easy you can see the colors. You can see the bright red leach cap here at the top. And then just below that, down in the floor of the pit, you can actually see a greenish color here. That's the oxide zone. So that's where you're getting these sort of secondary oxide minerals. And then just below that, in the middle is gray. That's the sulfide ore zone. So actually, just by color, you can kind of see that vertical progression down through the deposit. A couple of other features to point out. One, this is Cerro Colorado. That's what it's named after, the red hill. That no longer exists. That's been removed by subsequent mining. And the third thing to point out is this great big canyon that cuts right through the deposit here, which is known as the Quebrada Parker. And that's really important to the story here at Cerro Colorado. So the little cartoon I've got here is just to kind of show you the principle here. So I've got the y-axis is elevation. Obviously, we collected them as depth below ground surface, but then we normalize them so we could just have relative elevations of each of the samples compared to each other if we had multiple holes. So we've got elevation here against distance. So here we've got a single vertical drill hole, and we collected hematite going all the way down the drill hole. And what you would expect to find is that hematite would have precipitated first. The oldest hematite should be at the surface. That would have precipitated first. If you're raining down on this deposit, you'll precipitate hematite first here, and then things will keep percolating downwards. And you should expect things to get younger as you go down. And then what you would expect to see is a zero age at the current water table, because that's where you'd be precipitating new hematite today. So here's a picture of me sampling hematite in a core shed that was basically outside. So it was absolutely brutal working outside. And this was at Cerro Colorado in 2016. And here are some examples of some of the samples we collected. So this is on the left, we've got some samples from Cerro Colorado, and you can kind of see it's quite messy looking. These aren't pristine crystals. It's not like collecting a sort of a nice zircon crystal or something for dating. Most of the hematite is in veins. So this is a vein or a fracture surface, and the sample, the drill core is basically broken open, and you can kind of see it on the surface. Actually, some of the best hematite was the really black stuff that actually looks a lot like scoria, but it's actually hematite. And then what we end up dating are these little fragments of the hematite. So these are some SEM images of some of the grains that we dated. And then from Spence, this is a photograph from above of some of the drill cores. You can actually sort of see transect down through the core. So we've got gravels here on top, and then you can see the end of the gravel cover. Then we're getting into the leached cap zone, the weathered zone. And you can see there's a bit of a mixture here. We've got some copper oxides in here mixed in with some of the hematite. Then we keep getting deeper, we're getting a little bit more hematite. And the other thing to point out is you can actually see some of these breakdown relationships between primary sulfide minerals. So here's a pyrite crystal. You can see its original kind of cubic habit. And then you can see these little spherules of iron oxides and hematite that are precipitating directly from the breakdown of that pyrite. And again, here you can sort of see the original pyrite shape and then the secondary hematite growing within that crystal. And this texture here is often referred to as a boxwork texture. You get these sort of very cubic shapes, but they're all basically made out of hematite after replacing the primary pyrite. So how do we date the hematite? So we use a technique called uranium, thorium, helium dating. Uranium, thorium, helium dating is primarily used to measure cooling ages of minerals such as zircon and apatite. So that's where you probably mostly have heard about it. And the reason it's used to measure cooling histories is because it's a very low temperature thermochronology method. And it's basically, the principle of it is, if you have a decay of uranium or thorium or samarium as well, as they decay gradually from, in this case, uranium all the way down to lead, the daughter product, along the way, they spit out alpha particles, and alpha particles are essentially helium atoms. So during that long decay process from uranium to lead, you're spitting out a lot of helium. But because helium is a noble gas, most of the time that helium will just float off happily and exit the crystal. You have to get down to a pretty low temperature before that helium will be retained within the crystal lattice. So that's why it's used as a low temperature thermochronometer. In things like zircon, the closure temperature is about 190, 200 degrees C. In apatite, it's about 70 degrees C. So you have to cool these things very, very, cool them down a lot to be able to trap that helium. In the case of hematite dating, we're using it not as a cooling age, but as a precipitation age, because we're assuming that the hematite is actually growing in a cold environment way below the closure temperature for that system. Because we're up in the near surface environment, we're basically, at the surface or just below the surface at room temperature. And the closure temperature for hematite is a little bit tricky, but it's probably about 200 degrees C. So we're well below the closure temperature. So we're treating this as a geochronometer rather than a thermochronometer, and we're assuming that the age we get is the time of crystallization of that hematite. And this is just a photograph of a laser chamber. So one of the first things we do is we stick the grain into a planchette and we hit it with an infrared laser to heat it up. And that's how we extract all the helium, and we measure how much helium's in it. And then we dissolve the grain and run it through a mass spectrometer to measure the parent uranium and thorium. Okay, so this is back to our little cartoon, again showing, this is our cross section showing how we end up with vertical transect through the leach cap. And this is what we would expect to see if we plotted up the ages of this, if everything worked as it should, and we had progressive precipitation with depth from the surface downwards. So what we would expect to see is the oldest hematite at the top of the hole getting younger as we go down the hole, and we would expect it to come towards a zero age at the water table. That's what we would expect to see. Okay, so what do we find? So let's start off with Cerro Colorado. So just a reminder of where we are. So Cerro Colorado sits up here in northern Chile, just on the sort of western margin of the Altiplano here. So we're just kind of up on the western flank, and you can actually see it on Google Earth very clearly. Here's the pit. And just to remind you that there's this great big canyon whacking right through the middle of it here called the Quebrada de Parca Canyon. Cerro Colorado sits up at an elevation of about 2,500 meters, and it has a very deep water table, about 200 meters deep. And this is the results of our work, and this is from a couple of papers we published, one 2016 and one in 2021 with PhD student Joe Shaw, who did a lot of this work. And what we find is a very prolonged history of hematite precipitation at Cerro Colorado, dating back to about 32 million years ago is when we get the first precipitation. And for a really prolonged period of time, we're getting, there's obviously a spread through here, but we're the hematite is all being precipitated at roughly the same elevation. We're not seeing any real variation, suggesting that we probably had a fairly stable water table for a very prolonged period of time, and we were just precipitating hematite in that zone. But things then start to change, and of course, depending on your interpretation of this rather, messy data set, exactly where, roughly about 11 or 12 MA, we start to see a change, and we start to see a decrease in the precipitation of the hematite downwards, and that trajectory downwards roughly coincides with zero age, which is coincident with the elevation of the modern water table and the base of the Quebrada de Parca. So this is plotted relative to the modern water table, and the modern water table is being controlled by that canyon. So a couple of things to mention. Independent constraints on supergene enrichment at Cerro Colorado, and this is from dating potassium-bearing sulfate minerals such as alunite and jarosite. You can do argon-argon dating of those to figure out when you think supergene enrichment may have taken place. So those constraints suggest that the end of precipitation of things like alunite and jarosite happened around 14.6 billion years ago, whereas hematite continued to precipitate after that, suggesting that the precipitation of hematite isn't necessarily always directly tied to the timing of supergene enrichment. You could still generate hematite even after the enrichment is finished. So there are questions about why supergene enrichment ended when it did, and it's often linked to the idea that there was some kind of onset of aridity around that time, which basically means that the water is no longer there to drive that enrichment. But of course, that is complicated by the fact that you might have things like ignimbrites being deposited on top, or gravels being deposited on top that potentially could block the water from reaching the deposits. And so depending on where you are, that interplay between aridity and supergene enrichment is not always exactly clear. And that's one of the things that we're investigating. So potentially that could be the beginning of the onset of aridity. But it's not until about 12 million years ago, 10 to 12 million years ago, that it's thought that true hyperaridity, so down below 50 millimeters per year of annual rainfall, really started to take hold. And that timing coincides very neatly with the onset of incision of the Quebrada de Parca Canyon. And it's thought that that incision was actually triggered by a change in aridity And the way that the river responded, because the river does not have any water anymore to really transport material, but the Andes are still going up, so the rivers have to respond. The way that the rivers respond to the ongoing uplift with less water is they steepen up. So the Quebrada de Parca has a nick point that's still working its way up through the river. And so we were able to determine, that was in this paper, that's when canyon incision really took hold, and that was probably in response to this change in climate. And what we suggest is that incision of the canyon is what suddenly dramatically lowered the water table, and you can actually trace that with the hematite as it gets younger and younger as you go downwards in the vertical drill holes and trending towards zero age at the position of the modern water table. So what about Spence? So Spence is in a very different location. It's out basically in the middle of a sedimentary basin. It's quite far away from the Andean mountains themselves, and it's nowhere near a river. So the nearest river, the Rio Loa, is about 30 kilometers away. And so it'd be quite hard to argue that the any kind of incision or base level of that river is directly affecting Spence. And Spence is at an elevation of about 1,750 meters and a water table depth of about 80 meters versus 200 meters at Cerro Colorado. So Cerro Colorado again was up here, just on the edge of the Andes. Spence is out here, more out in the plains. And we get a different set of results here. So if you remember at Cerro Colorado, we have pretty consistent precipitation of hematite going back to about 32 million years ago. Whereas interestingly here at Spence, the oldest age we get is actually about 12 or 13. We think some of these deeper samples are from high permeability pathways where maybe we had fractures going quite deep that were allowing precipitation much deeper. The majority of the hematite, which is forming within the leach cap, started precipitating more like 10 million years ago. And interestingly, that coincides, the end of supergene enrichment here at Spence, actually, it stopped much earlier. And it's not really clear exactly what the control was on the end of supergene enrichment at Spence at that time. It's considerably earlier than it was at Cerro Colorado. So there's still questions. If that's climate related, then that raises some questions about why there'd be that variability. There could be other reasons. But the precipitation of the hematite has been very interesting because weirdly, it actually seems to start, we start getting the hematite precipitating shortly after the onset of hyperaridity, about 12 to 10 million years ago. And that shows that it is actually possible to have leaching, active leaching going on, or active hematite precipitation going on, even when you have a very arid climate. You can just about see, hopefully there is actually a little bit of a trend there as well. It's a little bit hard to pick out, but we do see a slight younging trend through the data there in that smaller window. So that's raised some interesting questions because basically what we're suggesting is that we were still getting leaching going on at Spence, even when the climate was already hyperarid. And we also know that it was buried under quite a lot of gravels by that point. So how was it getting the water? Where was that water coming from? So another thing that we did here is we looked at some oxygen isotope values for the hematite at Cerro Colorado and the hematite at Spence to try and see if we could distinguish different values of where the formation water may be coming from. And we were able to also then compare those with modern day oxygen isotope values for modern day rainfall. So we got elevation here on the y-axis versus oxygen isotope value on the x-axis, and it's lighter over to the left and heavier over to the right. And most of the modern day rainfall values up here at higher elevations. So you can see all these elevations, all the sampling points are up in the higher parts of the system, quite close actually to Cerro Colorado. And they're getting quite light isotopic values here. So the oxygen isotopes suggest quite light rainfall values, and they coincide fairly well with the values of oxygen isotopes that we get from the hematite that precipitated at Cerro Colorado. So the Cerro Colorado oxygen and isotope values coincide quite nicely with the rainfall trajectory. Whereas the the Spence samples here are slightly more complicated. What we find here is these are the values of oxygen isotopes from the hematite that we collected from Spence, and you can see that they're all much, much heavier, and they coincide very nicely with some isotopic work that was done by Karen Laybourne in 2005 from Spence, where they found two different types of water. They found isotopically heavier, what's known as formation water, so that's groundwater that's basically been transported a very, very long distance, and probably is upwelling. I'm going to show you the diagram about that in a second. But they also saw signatures of much lighter, isotopically lighter meteoric groundwater. They found both of those signatures at Spence. At Cerro Colorado, we're only really seeing the lighter isotopic numbers there. So what we think is that the hematite that precipitated at Cerro Colorado pretty much all derives from meteoric water and rainfall that probably fell pretty close to Cerro Colorado itself in the high Andes, and probably hasn't moved very far to get to Cerro Colorado. So some of the water at Cerro Colorado probably rained directly on the deposit, but we also know that it was blanketed by a couple of different ignimbrites, and there were gravels there too. So some of that water probably did come as groundwater filtrating into the deposit, but it hasn't transferred very far. Whereas at Spence, the signatures we get for all the hematite that we've analysed suggest that pretty much all of that hematite has been generated from formation groundwater, which is basically water that we think probably fell up on the high Andes, far, far, far away and a long time before, and has basically worked its way all the way down deep, deep, and then come back up. And the reason it's able to come back up and get to Spence is because Spence sits on the Antofagasta-Calama lineament through here, which is this major crustal fracture system, potentially strike slip fault system that provides a pathway for fluids to upwell along it and to provide water to Spence that would not otherwise be present, which allowed Spence to undergo leaching even long after aridity had started, and in theory the deposit had been kind of shut off from any water from above. So to conclude, to reach net zero, we need to find more copper. And again, to minimize environmental social impact, we need to find the absolute highest grade deposits that we can. And these high grade deposits often result from this secondary supergene enrichment process, which is driven by groundwater leaching. And what we found is that uranium, thorium, helium ages combined with oxygen isotope records of hematite within leach caps can track the movement of groundwater. And water tables can remain high in hyperarid environments if you have recharge by deep upwelling water, which means that weathering and potentially supergene enrichment, depending on how intertwined they are, can continue in an arid environment beneath cover. And this is important for exploration, because if we're thinking about finding more enriched deposits, particularly deposits that are buried under cover, which is increasingly becoming the case because most of the ones that are already exposed and easy to find have been found. If we want to find some under cover, we need to figure out whether or not we think that they potentially could have been, there could be the potential for any kind of enrichment, even after they maybe had been buried by an ignimbrite or gravels. Is there any potential that there could have been water that could have got into them from elsewhere that could have actually driven that leaching process despite the arid environment or the cover above them? So I think it has potential for thinking about future exploration. And so I'll just finally say thank you to Joe Shaw, who did a lot of this work as part of his PhD projects, and Byron Adams, who's been a big part of the project, and Laura Evenstar as well, who was at Bristol at the time. A lot of this work was done at the University of Bristol, so I cannot give lots of credit to UCL. I was at Bristol at the time. It was all funded by BHP, but we had a lot of support from NERC, and the oxygen isotope analyses were done at CERC, and also the uranium thorium helium dating was done at Caltech. However, I will just say that now I'm at UCL, we do have a uranium thorium helium lab, and we are in the process of building a new extraction line to date hematite and goethite and other mineral phases of interest. So if you're interested in doing this kind of work, I'm open to doing some new collaborations. Now I have my own lab to play with. Okay, thank you very much.